Hi everyone, today we're going to look at the composite Simpson rule. I'm going to go over a little overview of the theory and then I'm going to go ahead and do a question. In terms of the theory, the first main thing to note is it is an approximation method and we're working with pairs of intervals or pairs of values creating intervals. So if we have our curve looking something like that, while it's not exactly the trapezium method, if we go along here, we'll have a small amount of error, whereas if we go about here, we'll end up with a bit more, and here we have very small. And when it comes to the error, if we consider our delta term as the term by which it deviates from our curve for each interval, so we'd have delta 1, delta 2, we can say our total delta term is equal to the sum of the delta terms. And we can say, we put it as an absolute value, assuming worst case, where all of them are above the curve or all of them are below the curve. So that's generally how it works. It's important to note that our Simpson rule is dependent on our OH4 term, as you know from the Taylor series. So what's important to remember when we're considering that OH4 term, we can rewrite the approximate value over here as minus h5 over 90 times the fourth prime of a, where a is our value that we're looking at. And that is why you see it's integrally tied to the OH4 term. Now, to simplify this, to make this easier, rather than calculating the fourth prime of each term along there, we can state that if we know, we are able to work out the total error if we know, well, we can work out what it's going to be approximately equal to. It's going to be less than something. If we know what the maximum possible value of that is, then we can just multiply it by our term here, which comes from the Taylor series, minus h to the 5 over 90 times the max value on our interval a to b. So that's from our start to finish of the curve for f to the fourth prime of a, or of, let's call it x because we're looking between a and b, of x. And this is in absolute value. So bear in mind, this is how we work this out. Because we don't need the absolute exact precision, we know that we're going to deviate by less than this term. So with that in mind, we can then further state that that is going to be less than or equal to our intended error in our calculation. So if we were to derive that a little bit further, all of this is in your notes if you want to double check it. We can state that our delta H term, our delta term is we can say that it is less than or equal to h to the 4. I'm putting in absolute value as well. That minus, by the way, I'm going to just absolute value it away as well because we're looking at absolute value. So that we'll end up with, if you simplify it, h to the 4 b minus a over 90, over 180. Over here, b minus a over 2 is going to give you an h, so I've just converted one of the h's to a b minus a over 2. That's where we get that. And we'll end up with this term over here over 180, and then we mustn't forget our max term here, and I'm going to call that k. And that has got to be less than or equal to our epsilon. It's also important to remember that we can rewrite this h to the 4, but let me show you where it comes from instead. We know that h times the n terms, the n value that we use for the terms, is equal to b minus a over 2, because that's how we'll end up getting our h. This is by definition. We can rewrite it as h to the 5 times n over 90 times our k. And that is equal to our h to the 4 b minus a over 180 times k. And that's just by substituting this in if we ever need it. That's important to remember. Now, that's in terms of the error. Considering the actual formula, that is once again quite a straightforward and simple element that we're looking at. It's just something that we're going to apply every single time. So our formula in its raw form is we have our term from a to b, our integral of f of x, that is our function that we're interested in, dx. And I'm going to put an approximately equals to sign because we are approximating. It's going to be approximately equal to h over 3 multiplied by, and differentiating the brackets to make it clearer, y0 plus y2n. The 2n is because we are looking at pairs of terms, so this is our final term, plus 4y1, plus, I'm going to use some sigma notation here, just because it makes life easier. I'm going to go sigma from I equals 1 through to, I'm going to use a little n equals capital N. Our capital N we know is half the number of final terms. So we land up with that sigma of 2 times y to 2i plus 4y 2i plus 1. Oh, sorry, this n up here is n minus 1. Don't forget that minus 1 or you will have problems. And that is our equation. If you can get down each of these aspects, you will, and you understand where they come from and how to use them, you're going to be golden for the whole topic. So I'm now going to end this video and I'll start the next one covering a question.